Hello and welcome back to the final, I swear it's the last one this time, guys, video from the Fullerton College Pre-Press class on PIA's Pre-Press Training Manual, Section 4.1, Color Appreciation. I really enjoyed this topic, so I've taken my time. I'm very sorry these are such long-winded videos. Sorry, not sorry. This could be, and sometimes is, it's an entire standalone class. So I've done a lot of research on this topic, and I really do find it fascinating. I hope you do too. If not, you will. I'm shaking my fist, but the camera's off. Okay, so we've looked at the difference. Let's go back and look at this one more time between surrounds. In this image, you can see that though the green square or rectangles are all the same color, depending on the context they're in, they change significantly, which is to prove right here, the color viewing booth, what you want when you're seeing a proof. The booth on the left is clean and non-distracting, and it's perfect. It's just a booth, and you can put in what you want to see. The booth on the right is a realistic one from how they look in labs and print shops before you clean them off to show clients. Unfortunately, in any workplace, a table surface is an invitation to put stuff. And it's an uphill battle to keep a viewing booth clean and free and not covered in other people's stuff they just set down. But it's important because that surrounding clutter doesn't just make you look unprofessional, it actually affects how you see the color on the paper. So now let's talk about lighting. So that was the surrounding colors, because remember, human vision is very much built on comparison. And so to get the best view of how color works in a document is to view the document only. So all the relationships are only between different parts of the page, not between the page and that junk piled on the desk next to it. The other part that we can control is lighting. The temperature of light is extremely important. I have stories on this one because I've learned about this through multiple parts of my life. It's one of those weird things where all this random stuff I picked up from different places and different things I've learned and done all seems to point back to being extremely useful knowledge in printing. Go figure. So what matters in the right light temperature is the balance of red, green, and blue spectrum radiation. Because for us, the way our eyes are built, we see white when we see equal red, green, and blue light balanced the right way that our eyes are balanced, meaning a proportion that's equal to the proportion that is normally, or that we have our rods and cones in our eyes. So, color temperature. This is one of those things that I learned about in college when I was taking an astrophysics class for fun, because I like space, guys. It's cool stuff. And I didn't realize going into it, because I didn't know how astrophysics worked. I thought I'd be learning about gravity and how things interact and motion. But really, a lot of astrophysics comes down to spectrography. I'm probably butchering the word there. But a lot of astronomy and a lot of astrophysics is light-based, because most of what we know of outer space comes from those little tiny pinpoints of light that you can see on a good, clear, dark night. So we've made an entire field of science out of analyzing light spectrum to try and understand things about stars. In fact, about half that semester was spent learning about black body physics, which is to say, if you took a pure dark black ball of, let's say, iron, and you heat that up, it will change color at different temperatures. While it's still within a certain level of cold, and you might have seen this too at like a blacksmith shop or on a barbecue grill or something, if metal's still pretty cold, it's black still. When it heats up enough, the metal turns red hot. You can also see this from like pokers that you poke into a fireplace or at a campfire. If the metal heats up enough, if the fire is intense enough, the metal grill will start to glow red. After that, it glows yellow. After that, it glows white hot. After that, it glows blue. Anyways, that's also true of burning fires of anything. Colder fires, that's right, I said colder fires. You heard that correct. Colder fires like paper and wood, which only burn at like 400 degrees Fahrenheit, 451, if you've read your Ray Bradbury's. And if not, Ray Bradbury's a great author. Go read him. Take a break. Read some Bradbury. He's a good author. But anyway, sorry, coming back here, that's actually a cold fire. It only burns red and sometimes yellow. Hotter than that is white, like some butane torches. Hotter than that is propane and natural gas. Like if you look at a stove burner and it's burning blue, that's really hot. Anyways, so temperature and of actual physical temperatures and the light temperature are kind of correlated in science. So now we're talking about the temperature of the light being equal to a temperature in Kelvin, which is one of the measurements of heat you can have. So 5,000 Kelvin is the approved standard for viewing. It's a standard viewing lamp. It's not quite as bright as sunlight at noon, and it is brighter than a white fluorescent light. It's definitely warmer than light bulbs, the old incandescent ones, or even the new complex fluorescent light-saving ones. A lot of times LED lighting is too bright. It goes up into the tens of thousands because they're very blue and very bright. LEDs tend to lean that way. It's a struggle to get them neutral. We're getting better now, by the way. For the longest time, they were always kind of hauntingly blue. The light they gave off was ghostly. Anyways, you have to make sure the bulbs that you use are working properly. Make sure that there are ways of testing to make sure the color is correct. And they also make sure that you are seeing, or that they have had ample time to warm up and that they are changed regularly so they don't use an old worn out light bulb, which will not give you correct color. Remember that subtractive color, like printing, takes the light source that you're looking at and removes parts that you don't want to see. If you start out with too dim of a light, you're not removing it, or you're just not starting with enough colors. You're removing from it, but it's like, you're not getting as much back. I always have horrible analogies on this one. If you give your friend some money to go buy you a coffee, and then they get to keep the change for their troubles, and you send them off with a $5 bill, and they go to Starbucks, they're going to come back with like 25 cents. Gee, thanks, that wasn't worth my trip. But if you give them a $20 bill and send them to Starbucks, they're going to come back with almost $10. I'm making fun of Starbucks a little bit, but the point is you have to start out with more to have more left over, right? You don't go with a $5 bill to buy a coffee and come back with extra money, not more than a few cents if you're buying it at like a proper coffee shop. So the more you have to begin with, the better you are. Although you can also do too much. The stretching the analogy beyond its breaking point, you give them $100 and tell them to keep the change. They're going to end up with too much money for sending them just to get you coffee down the street at Starbucks. So if you start with too bright a light, it will still do weird things to your color. So you're trying to get the right amount for the right change that you're trying to see. I like this picture as well. Here's the same girl in her awesome 90s hair color. Reminds me a lot of Elaine from Seinfeld. You might notice there's a Seinfeld video in this particular class right now. Hee hee. Anyways, so the proof will look different under different lighting conditions. Fluorescent, it looks one way. Tungsten, which is kind of your standard light bulb that are mostly being phased out by today, and your 5,000 Kelvin. Same photo, different lighting. They look all slightly different. There's another video I've also put up on a good cheater way of testing your light. A way of seeing what kind of light is being given off by any light source. I know they're less common now, but you can buy them at Dollar Tree. It's even worth going to Dollar Tree and buying one with a movie or something on it, because who cares? Get yourself a CD or DVD you don't care about, and you can use it to refract the light of any light source. And by looking on the back at what kind of colors you see, you can either see that you have a spectrum of light, you can see what parts are dark on it and what parts are light. You can see if there's a continuous gradient of the whole rainbow, and then you'd see that under sunlight, where you'd see starting with violet and going all the way up through red, you'd see pure, no breaks, one continuous stripe of the same intensity of light the whole way across. But if you look at fluorescent lighting, you'll notice there are some gaps depending on the fluorescent light. Fluorescent light, by the way, I despise fluorescent lighting. It's awful and it ruins your vision and you don't get to see things. And it's being clinically proven to cause depression. I'm vindicated on this. I always thought it was depressing to be in a fluorescently lit place. But fluorescent light isn't white. I know traditional light bulbs, like the old Edison style ones, they're not white either, but they're different. You can really start to see this if you do some sort of refractive test with either a spectrometer or the back of a CD. You start looking at light sources. Incandescent light bulbs, as designed by Thomas Edison, the old ones with the carbon or tungsten filaments, those don't show you all the light. You don't get a whole rainbow, but the part that you get is continuous. You get a segment of the rainbow, and it may be kind of yellow and kind of dim, but the light that you see is all there. everything in between. Fluorescent light plays with human perception because if you know anything about how light works, I don't necessarily want to go to a long physics lesson here about how cathode ray tubes work, but it's different science. When you put an electrical charge through a regular light bulb, like an incandescent one, it's basically a toaster coil in there. The filament that gives off the light in a regular incandescent light bulb is a resistor. The electricity doesn't flow through cleanly, and the resistance it gives turns into heat energy, and that lights it up. So it heats up, and that light, that's why light bulbs are hot, traditional ones anyways. And so when you have that, then falls back onto the chart of black body physics. That is light being given off by a warm, glowing, hot substance. And that gives off a spectrum, but it gives it off continuous. Even if it's not that bright, it's a continuous spectrum of all the colors within the space it can show you. However, if you use fluorescent light, it's basically a form of neon lighting. And neon and fluorescent lights give off line spectrums. Honestly, go find yourself a fluorescent light bulb and look at the light it's giving off using that CD technique. You're going to see a distinct line or two in red, in green, in blue. When you put electrical charge through a condensed gas inside a tube, which is how those things work, it doesn't heat it up. I mean, it heats up a little bit, but it doesn't heat it up and cause it to glow by heat, by resistance and resisting. Instead, it charges the actual electrons inside the gas itself. It adds energy to the atoms, to the elements that are the gases inside. And when those things, it artificially bumps the electron from one orbit to a higher energy state. And as the energy diminishes, those electrons don't stay in those orbits. They fall back to the lowest possible orbit around the neutrons and the protons, around the nucleus of those atoms. And the distance between where they start and where they fall back to from the charging actually is the wavelength of the light that they give off. That's why some neon lights give off one specific color. You see different colored neon lights. Each one of those is a different type of gas, and the gas inside has that level of difference between its electron orbits that actually correlates to the color of the wavelength of the light that's coming out. Fluorescent does 3. It's 3 gases, or a gas that gives off 3, and it's line spectrum. It looks white to you because you're seeing red light, green light, and blue light at the same time, but you're not seeing all the light in between. You're only seeing the 3 primaries, and it can be different parts of the primaries too. Did you know that they screw with you? Sorry, they mess with you and cheat you a little bit at grocery stores using the lighting. Also, you already know that there's a difference in fluorescent lighting, by the way. If you ever walk to a Big Lots, the lighting in there is fluorescent, but it's always this gross brown yellow color. It always feels kind of icky and dirty, even if the store is brand new, because they use such cheap lights in there. And if you go to like the makeup aisle at Target or something, then suddenly the light's all bright and clean and bluish white, and you feel so clean and so futuristic when you're walking down those aisles. But also, grocery stores do in-between things between those as well, because depending on the exact balance of gases inside that tube, and depending on exactly what spectrum of lights it gives off, even though it's appearing mostly white to you, it can lean one way or another. If you're selling things that are clean and white, you want that to lean towards the blue light. Then if you're selling paper or, cloth goods, there's not a whole lot of things you really want that for. Things appear brighter and cleaner. Now, if you're in the produce section, people are looking to buy green, fresh lettuce and green, fresh vegetables. And you can tell by how green they are versus how yellow or brown they're turning, how fresh your produce is. So in those sections of the store, the lighting leans green. That's why you buy what looks like super fresh green bananas at the store, because you don't want them to go bad that night. You get them home and they're like, how'd they go yellow already? I thought they were green. Well, they looked green because the light was green you were buying them under. And likewise, you have the similar problem buying meat from the meat section. If you're not a meat eater, I apologize. But they do make sure that the fluorescents lean red so that it appears fresher and redder, rather than dull gray and brown like when you get home. So I'm going to have to do a 6th video. I'm so sorry. I know I talk on and on about this. I'm very excited about it. That's why there's only 1 video this week. Again, come back for 1 more, and that one will be shorter. Let me pause here and we will pick up in a moment.